All right, let's talk AI. We're always focused on the brains, right? The data, the fancy algorithms, but today we're going to go under the hood. We're diving into the secret world behind artificial intelligence to find the invisible engine that really powers it all. And, more importantly, why the language it speaks has these profound and often hidden ethical consequences. Let's get into it. So, let's just chew on this for a second. We spend so much time talking about the high-level ideas of AI, but the real story, the thing that connects a brilliant concept to a real-world action in your car or on your phone, it's happening at a much, much deeper level. And that's where the risks and, frankly, the responsibilities really are. When you think AI, you probably think Python. And yeah, for all the research and the cool prototypes, that's true. But that's just the tip of the iceberg. The reality is, the industrial-strength AI that's actually running out in the world, in cars, in trading systems, in medical devices, that's all powered by a high-performance C++ engine. Think of it this way. Python is the architect with blueprint, but C++ is the crew that actually builds the skyscraper. Okay, so why does split? Why do these, elegant ideas from data scientists have to get translated into this beast of a language? Well, it all comes down to the brutal, unforgiving demands of the real world. It really comes down to two things: performance and control. I mean, think about it. When you're talking about robotic surgery or a self-driving car slamming on the brakes, you can't have a delay. A millisecond pause, caused by something as normal as Python's garbage collection, cleaning up memory in the background, that's not just an inconvenience. It could be a catastrophe. C++ gives you that predictable, lightning-fast speed and total control, which is exactly why it's the engine behind huge frameworks like TensorFlow and PyTorch. Okay, but here's where it gets really interesting, and honestly, a little scary. This setup creates a dangerous gap, what some experts are calling an ethical air gap. The original intent of a model, something carefully designed by a researcher in Python, can get subtly twisted or even totally lost when it gets re-implemented and optimized in C++ for the real world. Something always gets lost in translation. And this right here is the absolute heart of what we're talking about today. How do these seemingly neutral technical decisions, choices made just to make an AI faster or smaller, how do they end up literally building bias and discrimination right into the code itself? I mean, just picture it. You have this massive AI model. It's gigabytes in size, and you have to somehow cram it onto a tiny chip in your phone or your car. It's kind of like squishing a huge, beautiful photo down into a tiny thumbnail. And what happens when you do that? You lose detail. The big question is, what details get thrown out first? And this is where the penny drops. Models are trained using these super high-precision numbers that can capture all kinds of subtle nuances in the data. But to make them fast and small, they get converted to low-precision formats. The first things to go are often the most subtle details. And guess what? Those subtle details are often the very patterns that help the AI recognize underrepresented groups. Some researchers are even calling this minority erasure. So let's get specific. This table breaks it down perfectly. You have these two totally standard C++ tricks: quantitation and pruning. When an engineer prunes a network, they're basically just snipping away the weakest connections to save space. But what if those weak connections were the ones that learned to recognize less common examples? Suddenly, your optimization just became a form of automated bias. And look, this isn't just some abstract, theoretical risk about fairness. This is about physical safety. When code goes wrong in C++, it can be catastrophic, and we have a chillingly perfect historical example to prove it. You might have heard of the Toyota unintended acceleration case. It's become this infamous blueprint for software disaster. And here's the kicker. It wasn't a sticky gas pedal or a mechanical problem. It was a software failure. Pure and simple. Investigators dove into the C++ code and found what they called spaghetti code, a tangled, unmaintainable mess where a single memory bug could just silently change the number controlling the throttle. And the scale of this, it's just mind-boggling. Over 10,000 global variables. What does that even mean? It means no single human being on the planet could possibly understand how that system actually worked. It wasn't just code, it was a ticking time bomb, written in C++. So here's the bottom line. You can have the smartest, most brilliant AI in the world, but if the C++ foundation it's running on is a house of cards, then that intelligence means nothing. A simple memory bug can completely hijack the AI's thinking and lead to disaster. Okay, so that's the problem. It's a big one. So what do we do about it? This brings us to the most important part, the solutions. How do we turn this around? How do C++ developers become the guardians, the sentinels of AI? Well, the good news is we don't have to reinvent the wheel. The answer is in the kind of super disciplined engineering that's been used for decades in aerospace and medical devices. We're talking about following strict safety standards, using coding rules that flat out ban risky moves, and even using math to prove that the code is safe before it ever ships. So what does this mean for the developer on the ground? It means they have this direct ethical duty. They have to audit their own work for fairness, not just for speed. They have to plan for what happens when things go wrong, making sure the system fails safely. And they have to be absolutely paranoid about every single piece of third-party code they pull in, because a weakness anywhere is a weakness everywhere. Which brings us to this final, really critical question. An AI model, it's just a piece of math. It makes a prediction. But it's the C++ developer who writes the code that turns that prediction into a real-world action, steering a car, approving a loan, making a diagnosis. So as these systems get more and more autonomous, the spotlight of responsibility starts to shift. It moves away from the abstract algorithm and shines directly on the code itself. And it leaves us with a really tough question. When it all goes wrong, who is truly responsible?